Sample mean. In the previous lecture, we see that sampling distribution of when population is normally distributed. But when the population is not normally distributed, when the population is not normally distributed, if all the samples of size n drawn from the population of size capital N with mean mu and SD sigma, then the mean and SD, that is standard deviation of the sampling distribution of sample mean are as follows. In case 1, sample mean is mu and standard deviation is sigma by root over of n into root over of capital N minus small n by capital N minus 1. If capital N is finite and sampling is under SRSWOR, and case 2, sample mean is mu and standard deviation is sigma by root over of n when n is infinite. And the third case is sample mean is mu and standard deviation is sigma by root over of n. Here sampling is under SRSWR. That means in the both case, second case and third case, the sample mean is mu and standard deviation is sigma by root over of n. Now we know about central limit theorem. Central limit theorem. We have to know that central limit theorem for large values of sample is for large values of sample size n. So it is greater than is equals to 30. Then the sampling distribution of sample mean is approximately a normal distribution. Irrespective of population. For example, say we let here the population of size 5, that means say the populations are 11, 8, 6, 3, 2. This is the population of size 5, and from here the population mean, that is mu is equals to 11 plus 8 plus 6 plus 3 plus 2 by 5, that is equals to 6, and population variance, which is equals to sigma square, that is 11 square plus 8 square plus 6 square plus 3 square plus 2 square by 5 minus 11 plus 8 plus 6 plus 3 plus 2 by 5 whole square. From here we get, that is 10.8, and SD, that is sigma, which is equals to root over of 10.8, that is 3.29. And From this population, if we draw the sample of size 2, the possible samples are number of possible samples are 5 square, that is 25. And now we can write here what are the population, what are the samples. Means 25 samples are, we write here all the samples starting from 11, that is 11 11, 11 8, 11 6, 11 3, 11 2, next 8 11, 8 8, 8 6, 8 3, 8 2, then it is 6 11, 6 8, 6 6, 6 3, 6 2, then it is 3 11, 3 8, 3 6, 3 3, and 3 2, and lastly it is 2 11, 2 8, 2 6, 2 3, and 2 2. These are the 25 samples, and the corresponding sample means are from this. The means is 11, this is 9.5 for this one, this is 8.5, this is 7, this is 6.5, then this is also 9.5, this is 8 7, this is 5.5, this is 5, this is 8.5, this is 7 6, then 4.5, then 4, then 7 5.5, 4.5, this is 3, this is 2.5, and this one is 6.5, 5 4, 2.5, and last is 2. So these are the 25 sample means. Now we write the distribution of sample mean, that is x bar. Sample mean. Now x bar, the probable sample means and the probability. Here the sample means are 11 9.5, then it is 8.5, then 8 7, 6.5, 6 5.5, then 5 4.5, 4 3, 2.5, and 2. And there are 25 outcomes. Out of 25, 11 is one time, so probability is 1 by 25, and 9.5 is 2 by 25, 8.5 is also 2 times, so it is 2 by 25, 8 is 1 time, so it is 1 by 25, but 7 is here 4 times, that is 4 by 25. And about 6.5, there is 2 times 6.5, that is 2 by 25. 6 is also 1 time, so it is 1 by 25. 5.5 is also 2 times, so it is 2 by 25. 5 is also 2 times, so it is 2 by 25, and 4.5 is 2 by 25. 4 is also 2 times, so 2 by 25, but 3 is 1 time, so it is 1 by 25. 2.25 is also 2 times, and 2, that is also 1 time. Now from here, in the previous example or from the theorem, you can find the expectation of sample mean, expectation of x bar square, and from here variance of x bar, variance of sample mean, that is the formula, that is x bar square minus e of x bar, and is d of x bar, that is root over of variance of x bar. This, all these values you can find it. Okay, this is your homework. Now we start from sampling distribution of sample variance. Now we in the previous example we we find the sampling distribution of sample mean, but here we find the sampling distribution of sample variance. If A square, capital A square be the sample variance of a sample of size n, small n, drawn from the population with mean, mu and standard deviation sigma, then expectation of sample variance, this is equals to n minus 1 by n into sigma square, where population size is infinite, or sample is drawn with replacement. That means after each drawing the population size is same. We prove this one. Let x1, x2 up to xn be the sample. So we find here a square is equals to, from the formula variance, this is 1 by n summation of I is equals to 1 to n xi minus x bar whole square. Okay, here x bar is the sample mean. Now by central limit theorem, x bar has approximately normal distribution with mean mu and SD sigma by root over of n. So expectation of x bar, that is equals to mu, and expectation of x bar minus mu whole square, that is equals to sigma by root over n whole square, that is sigma square by n. As standard deviation is sigma by root over of n, and we know this is the formula variance, so variance is equals to standard deviation whole square, that is sigma square by n. Now since xi varies over the values of population, so xi has same distribution as that of the population. So variance of xi, this is also sigma square. Now if I write, this is the equation number 1. Now from 1 we can find s square is equals to 1 by n summation of I is equals to 1 to n xi minus x bar whole square. Now this is can be written as 1 by n summation of I is equals to 1 to n xi minus mu plus mu minus x bar whole square. We can add here minus mu and plus mu. So from here this is can be written as summation of I is equals to 1 to n. This is split by xi minus mu minus of x bar minus mu, this whole square. Then we split here by a minus b whole square. So it is 1 by n summation of I is equals to 1 to n. This is xi minus mu whole square minus 2 into xi minus mu into x bar minus mu plus x bar minus mu whole square. Now if we split the summation, this is 1 by n summation of I is equals to 1 to n xi minus mu whole square minus 2 into x bar minus mu, as it is a constant part, so it is in the outside of the summation, that is 1 by n summation of I is equals to 1 to n xi minus mu plus 1 by n summation of I is equals to 1 to n x bar minus mu whole square. Okay, so from the first part, this is the same, say it is summation of I is equals to 1 to n xi minus mu whole square minus 2 into x bar minus mu into, this one can be split by 1 by n summation of I is equals to 1 to n xi minus 1 by n summation of I is equals to 1 to n into mu plus 1 by n, and this, as this is the constant, so this is n into x bar minus mu whole square. So from here this part is same, summation of I is equals to 1 to n xi minus mu whole square minus 2 into x bar minus mu. We know this is x bar and this is 1 by n into n mu plus, from here n cancel, this is x bar minus mu whole square. So this is 1 by n summation of I is equals to 1 to n xi minus mu whole square minus, this is n cancel, so it is 2 into x bar minus mu whole square and it is x bar minus mu whole square. So we get this one, minus x bar minus mu whole square. This is the value of s square. Now if we find the expectation of s square, that is E of s square, which is equals to 1 by n summation of I is equals to 1 to n expectation of xi minus mu whole square minus expectation of x bar minus mu whole square. Now this is the variance, formula of variance. So 1 by n summation of I is equals to 1 to n, this is variance of xi minus, and this is sigma square by n, as we find here, that is this value is sigma square by n. So we write here, now 1 by n, we know variance of xi is sigma square, so we can write here summation of I is equals to n, this is sigma square minus sigma square by n, that means 1 by n into n sigma square minus sigma square by n, that means sigma square minus sigma square by n. So we can get this one, that is E of s square is equals to this. We prove it. Okay. Now from this we can deduct so many formulas. If say in the for an example, say this is the example, that is a normal population has a mean 0.1 and standard deviation 2.1. Find the probability that the mean of a sample of size 900 will be negative, given that probability of mod z less than 1.43 is equals to 0.847. Here, since the population is normal and the sampling is random, it is given here that is normal population, and we find here the normal random sampling. So since the population is normal and the sampling is random, so the sampling distribution of x bar, that is sample mean, is normal distribution with mean is equals to population mean, because we know that in that theorem, that is sample mean and population mean is same, that is mu is equals to 0.1, which is given here, and standard deviation is sigma by root over of n, that is 2.1 by root over of 900, which is equivalent to 0.07. So the standard normal variate, that is z is equals to x bar minus 0.1 by 0.07 is a standard normal variate. But because in normal distribution, if x is the normal variate, then standard normal variate is z is equals to x minus mu by sigma, where mu is the mean and sigma is the standard deviation. So we find here z. Now we have to find out the probability of sample mean is negative. That means the sample mean is negative. So it is x bar less than 0. We find this probability. And so when x bar is equals to 0, then what is the value of z? Z is equals to 0 minus 0.1 by 0.07. That is equals to minus 1.43. So probability of x bar less than 0, this is equals to probability of z less than minus 1.43, which is the area under the normal curve on left side of the coordinate z is equals to minus 1.43. If we draw the picture, then this is when we find the normal distribution, the curve is bell shaped. Bell means ring bell. Okay, say it is 0, and say if this value is 1.43 and if it is minus 1.43, then our area is this left side of what we write here, that is left side of z is equals to minus 1.43. That means our area is from minus 1.43 to minus infinity. Okay, so from the figure, probability of Okay, what is given here? That is probability of mod z less than 1.43. That is equals to 0.847. This is given. Okay, that means from here we can write probability of minus 1.43 less than z less than 1.43. This is equals to 0.847, because if we know that mod z less than 1 means minus 1 less than z less than 1. So from that series theorem we can write this one. Okay, so the area under the normal curve, which is shown in the figure, enclosed between the two ordinates z is equals to minus 1.43 and z is equals to 1.43 is 0.847. It is given here. And now the area under the normal curve on the left side of y-axis is 0.5. That is from 0 to this one. 0 to minus infinity. This value is 0.5. Total value is from minus infinity to plus infinity. It is 1. And so as it is a symmetric distribution, normal distribution is always symmetric distribution. So from 0 to minus 5 infinity, what is the value is equal to 0 to infinity. This total value is 1. So 0 to minus infinity, this value is 0.5. So we find the probability of z less than minus 1.43. This is the area on left side of the ordinate z is equals to minus 1.43. That is total is 0.5 minus this value, that is total value. So okay, we know this value. This total value is 0.847. So that means this half value, this is the half value. That means half of 0.847. Okay, that means total is 0.0765. Hence the required probability is here, the required probability is equals to 0.0765. That's it.